So I feel like we have just kind of cruised, kind of covered some important topics in chemistry, and after we covered physics, and then we're going to cover astronomy and meteorology and then earth science. So one of the important topics in chemistry is this concept of a mole. And so we're going to look at that. So a mole actually is important in chemistry. A mole is important in chemistry because things in chemistry are very small. And I haven't really been able to kind of show you how, or kind of relate to you how small an atom is, for example. But if you have like 12 atoms, okay, like together, you really can't even weigh that. You can't really see those 12 atoms, okay? So instead, we kind of scale it up. So we got this idea of a mole. Now, we haven't done a lot with scientific notation numbers, but in order to understand a mole, you're going to have to kind of go with this whole idea. This number is packed up in scientific notation. So 6.022 times 10 to the 23rd, okay, what does that mean? Let's go ahead and unpack it. We could write the coefficient 6022, okay, and of course the decimal is kind of is here, and then we need to move it over 23 places. So here you go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right. Then we get to put in zeros. Something like that, okay? So that is a mole. That number right there with the decimal over here, that's a mole. It's a big number, okay? We haven't done a lot with equivalency statements, but this is an equivalency statement, 1 mole of anything. And I'm going to kind of turn to rice grains here in a minute, but usually it's 1 mole of atoms. 1 mole of anything is equal to 6.022 times 10 to the 23rd counted particles of those things. So actually I have a couple visual examples though. So atoms are really small, but even though that number is really big. So this actually is copper. Okay. And I'll pass this around. Those are copper atoms. It's a pure sun. This is copper. And actually, that is 1 mole of copper atoms. Now, and we're going to show you how you can get that, how you know what mass to weigh up to get 1 mole of copper atoms. And then here's another one. This is water, I promise. Okay. This is actually, you know, we've looked at the water molecule, H2O molecule. These are repeating units of H2O molecules. And this is also a mole of water molecules. So we usually use a mole in terms of atoms and molecules, right? Okay. The 6.022 times 10 to the 23rd, there's a scientist, I don't know his first name, but his last name is Avogadro, okay, way back when. And actually, he's accredited with coming up with this number, and so it's called Avogadro's number. And it's based on in science we always have to have some kind of standard that we can go back to. It's actually based on the element carbon, one particular form of carbon, carbon 12. The abbreviation for a mole, it's one of my favorite. I think we talked about abbreviations. You get to drop the E. Instead of M-O-L-E, it's M-O-L. You're like, oh, that's kind of fun. I wonder who thought of that. Okay. So, like I said, you know, you could count like 6 atoms, but you wouldn't really have anything you can sink your teeth into. You can count 12 atoms, but really you're not talking about anything you can weigh, anything you can do anything with. Okay, but you add them up. So a mole is a counted number of particles. You're familiar with a dozen has 12 things. If you have a dozen of anything, a dozen eggs. Okay. I don't know if you're familiar with the gross, but a gross is 12 dozen, so 144 things in a gross, like a gross of pencils. Okay. And then, of course, we have a mole of anything. That's 6.022 times 10 to the 23rd of anything. Okay. And usually it works real well for small particles. So, but like I said, kind of scaling it up and being kind of silly, starting with rice grains, right? This is to try to give you a sense for kind of when you have a mole of anything, what you've got, right? So I have some things up here that relate to rice grains and moles. So what I have here is rice grains, uncooked rice. And this is 10 grains of rice. Okay, 1 times 10 to the first. And this is 1,000 grains of rice. 1 times 10 raised to the third power. So 10 and 1,000. And then this sack right here, okay, I have it listed, this sack right here actually is 2 times 10 to the fourth rice grains. So 2 times 10 to the fourth, okay, that's 2 and move the decimal place over 1, 2, 3, 4, put zeros in there. Okay, of course that's 2,000. 2,000 rice grains right here. Okay. Now here in a minute I'm going to show you how you can go from like counted particles, 2,000 rice grains. How many moles is that? And actually that is 3.3 times 10 to the negative 20th moles. So this is a fraction of a mole. 0.000000033 moles. A lot of eggs. So if you were to have a mole of rice grains, okay, and you just put it on the land area, and some of you guys know, and we'll talk about this in meteorology because it's a little bit of a player, most of the earth is covered by water, okay? But if you were to cover the land masses we have now would be up like 75 meters, okay? So 1 mole of rice grains over all possible land. Like, oh, that's problematic. It is problematic. Again, with the rice grains, as much as we like rice, and it's a great staple, it grows real well, and a lot of cultures have used it as a staple in their diet. Not as many rice grains have been grown since the beginning of time. I guess since people have been eating rice. Okay, so that's not happening. Again, with the rice grains, if you were to combine a mole of rice grains to a cube, it actually would be 120 miles on all 3 sides. Like, whew, a lot of rice grains. Now switching gears. I always think of like the Ghostbusters movie and the Stay Puft Marshmallow. Don't think of anything, clear your mind. He thinks of like the Stay Puft, yeah. A mole of marshmallows would be problematic because just confining it to the United States, it would cover us in a depth of 600 miles. Okay, a mole of marshmallows, don't even think it. Snowflakes, we know about here in Iowa. Now, snowflakes have different densities. Sometimes they're dense, and sometimes they're light and fluffy. But just in general, if we had a mole of snowflakes, which seems like it would be doable, it would cover the United States, again, up to the depth of about 2/3 of a mile. So don't count on a mole of snowflakes either. Okay, but this is a mole of atoms, mole of copper atoms. This is a mole of water molecules. So that kind of just gives you a little bit of an idea here. If we were going to try to count a mole, like 1, 2, 3, 4, 5, 6, count up to 100, count up to 200, count up to 1,000, count up to, 10,000, count up to a mole, you could like have everybody help count it, but at the time this was written, you would have to have everybody on Earth counting, and times 51,000, and it would take 75 years if that's all they were doing, like no sleeping or anything. So that's a mole. That's a big number. It is totally a big number. Okay. Again, with the counting, there's this very fast computer here. If you were to have a computer to go ahead and kind of do 1, 2, 3, 4, have a computer do it, it actually would take, this is the same computer that's very fast, could count the entire population of the United States in less than a second, less than a second, how many people in the United States. Well, if it was going to count a mole, it would take it 1.9 million years. I know. And actually, I've worked this out, this kind of using factor label. I'm like, really? Yes, 1.9 million years, even though it's a very fast computer. Hockey pucks, if you had a mole of hockey pucks, it would be equal in mass to the moon. Basketballs, the volume would be the size of the Earth. Okay, this is one of my favorite, a mole of pennies. Now, if you're like me, you see a penny and you're like, I usually see if it's heads up. And then, and if it's heads up, I sometimes like leave it for the next person. I guess if it's tails up, I should flip it over and make somebody else smile. I don't know. But pennies, I usually just vacuum up or whatever. But if you had a mole of pennies, which seems like a lot of money, you just move the decimal place over, 2 places, and that's how many dollars you have, right? So here's the deal. At the time this was written, you could actually divide that mole of pennies to everybody, and everybody gets their fair share. And the deal is that every person who got their portion of a mole of pennies, they could spend $1 million a day, okay? And actually that would take them into 4,000 years from now. They could spend $1 million a day. I don't know what that would do to the economy, but you can see that actually the problem with having a mole of pennies, and this kind of reminds me of the show Genie. Did you ever see where they would like wish for things and they would come true and they would be bad things? So a mole of pennies actually would cover all the land area again up to a depth of 420 meters. So moles are meant for little things, okay? Okay, so let's do a couple of problems. Anybody want to borrow a calculator or your phone works? Or you will need scientific notation, so. So we haven't done, I kind of haven't emphasized what I call the factor label method of working problems too much in here. But, so let's look at these. And let's eyeball them, and then we'll use the factor label method. So we've been talking how 1 mole, I'll put it up here. I guess I'll put it up on the whiteboard. Okay. A few slides ago, we've been talking about the concept of a mole. And 1 mole, 1 MOL, is equal to 6.022 times 10 raised to the 23rd power of anything. And I'll go ahead and call it atoms. Okay, 1 mole is equal to 6.022 times 10 to the 23rd atoms. How's that? So here in the first problem, they say a sample has 3.011 times 10 to the 23rd atoms. How many moles is in this sample? Does it seem like about a half? Do you see where if you compare 6.022 times 10 to the 23rd times 3.011, I picked that on purpose. Does that seem like a half? That's the answer. 0.5 moles. You have a half a mole. I'm going to show you how to do that, kind of what I call the factor label method. That is the answer, though. And remember, as long as you kind of show me your thought, or for sure show me units. I'm not going to be too picky how you work things. But this is how you would work it using the factor label method. The first term actually would be, I'll pick blue, 3.011 times 10 to the 23rd atoms. And I would put that over 1. It's just how I work these sort of problems. Okay. And then I would actually use this equals statement up there, and I would bring it down, okay? And I would recognize that there is 1 mole. I'll put 1 mole in the top over 6.022 times 10 to the 23rd atoms. That's the definition of a mole. And by golly, let's all check our calculators. And the scientific notation part, this is kind of nice because actually if you're into doing such things, you see 10 to the 23rd actually could cancel out for this sort of problem. The other thing that cancels out, though, that's why I like working problems this way. The other thing that cancels out actually are units. So units of atoms cancel out. Do you get 0.5?
No, I got 5.5. So maybe if we just switch it around where 6 is divided by 3.
I don't know. I do that. Try it one more time. Because it's like balancing your checkbook. How many people got 0.5? Yep. So why do you have an answer there divided by?
Because I equaled it. Because otherwise it's too much information into one thing.
Okay. Well, we can look at, let's do the next one, then let's double check. Okay. But it is 0.5. The answer is 0.5. Okay. So if we do the second one similarly, now we can't just eyeball the second one. I did that on purpose. Direct. Oh my gosh. But notice that we have more atoms. The number of atoms we have now, let's see, how many moles of carbon atoms are present in, oh goodness, looks like I got in a hurry there. This word moles, actually moles of, this should go away. Sorry, my bad. That reads better. How many moles of carbon atoms are present in 5.45 times 10 to the 24th carbon atoms? Much better. Okay, so the number of carbon atoms we have is 5.45 times 10 to the 24th. So does it sound like it should be more than a mole? Because 10 to the 24th is more than 10 to the 23rd. I'm just kind of eyeballing it at this point. Seems like it should be more than a mole to me. Okay, so if you're stuck, you're like, how should I work this problem? Well, just divide numbers so you get a number that's more than 1. Okay, but I'm going to show you actually, again, I'm going to use this pattern up in blue. I had it in blue up here. Okay, now we haven't done many chemistry problems. This is one chemistry problem I kind of wanted to get to. So my first term is going to be that 5.45 atoms, carbon atoms or atoms, over 1. Oops. 5.45 times 10 to the 24th. Okay, and then again, I'm going to put 1 mole over 6.022 times 10 to the 23rd atoms. And again, with this sort of method, we're wanting our units to cancel, so our units of atoms cancel, which is awesome. And we have units of moles, which is... And we talked in the physics unit of, remember, kind of rounding, giving it the fewest decimals. So, gosh, it looks like we could go with 3 decimals. The previous one, we could have gone with 4 decimals. So actually it was 0.5000. The sun's coming out. Okay. I got 9.05. And units would be moles. What do you think? Ooh, naked number alert. Any questions about that? In all sort of problems, it helps just to kind of look, does it seem reasonable? It seems reasonable. Okay, so a mole is a lot of particles, 6.022 times 10 to the 23rd. We can actually take a number of atoms and pack it up into moles. Okay. The next one actually is take a mole and to kind of unpack it into the number of atoms. That's the next one. So what if we're dealing with the element barium? Could be any element, but we're just dealing with barium. And how many barium atoms do you have if you have 2.5 moles of barium? Well, let's see, 2.5. If, I'll put at the top again what the definition of a mole is. If the definition of a mole, 1 mole, is equal to 6.022 times 10 to the 23rd atoms. If I have 2.5, it seems like I should have 2.5 times 6.022 times 10 to the 23rd, and that is actually the right answer. If you take 6.022 times 10 to the 23rd times 2.5, that's how many atoms you have. I'm going to show you, though, what that looks like if you're using the kind of what I call the factor label approach to working. So in this approach, we always start with the number that you want to convert, which is 2.5 moles over 1. And again, I'm going to use that equivalency statement at the top right-hand corner. But I'm going to use it so that moles cancel. So I'm going to put 1 mole on the bottom, and on the top I'm going to put Avogadro's number, 6.022 times 10 to the 23rd atoms. You know, you'll run into one of these on a test most likely, and it's like, if you don't set it up like this, that's fine. But you just need to be able to get the right answer. Okay, so setting it up this way though, looks like our moles cancel. We're left with units of atoms. And times 2.5. Does it seem right? We should only give us 2 decimals. Okay. So it's going to be a big number. So 2 decimals, I got 1.5 times 10 to the 24th. Which seems reasonable. And units, of course, no negative numbers are atoms. See, in chemistry, and we didn't really get to it too much because we didn't have much time, but in chemistry, a lot of times it's very important to count particles. We need to be able to count them. It's not just about grams and liters. It's about counting atoms and molecules. All right, so the last one here, switching it up from barium to selenium. And how many atoms are there in 0.00912 moles? So it's going to be less than 6.022 times 10 to the 23rd. Actually, if you would take Avogadro's number, 6.022 times 10 to the 23rd, and multiply it by that 0.00912, you would get the right answer. Okay, that's totally right. And here's what it looks like set up. So we go, the first term is 0.00912 moles over 1. And the next term is that I want moles to cancel, so I'm going to put 1 mole on the bottom. And I can put Avogadro's number on top, 6.022 times 10 to the 23rd atoms. I did this so moles will cancel. We're left with units of atoms, which is awesome. Looks like we're going with 3 decimals again. Remember how we count this? The 0.00912, actually, the only cool digits are the last 3 digits. 0.022 E23 5.00912. We said 3, so I got 5.49. Times 10 to the, now don't forget that part, times 10 to the 21st. A good thing about showing your work is if you forget for some reason to write down this part right here on the test, I'm like, oh, wait, no, they knew what it was. Do you know what I'm saying? So showing your work, you can't go wrong. I think I lived on partial credit for some of my classes. Okay, so this will be due on Wednesday. I know it says exercises, but it's only exercise. So page 393, exercise 118. Concept of a mole, gotta love it. It's a big number, big counted particle. So one more thing before we leave chemistry I want to talk about is related to a mole. Okay, there are certain things. Sometimes it's hard. You know, you read a word. You know the word, and you're like, well, what is the definition of that word? I like it because kind of the definition of this word is in the word. So in chemistry, there's something called the molar mass. The molar mass is something. Molar mass is the mass of 1 mole. Molar mass is the mass of 1 mole. Okay? So honestly, remember I've kind of passed these around. This was copper. Molar mass, the mass of 1 mole. I told you this is 1 mole of copper atoms. If we were to weigh this, that is the molar mass of copper. Mass of 1 mole. And actually it's like 63.45 grams. Okay? I said that this was 1 mole of water molecules. 1 mole, okay? So if this is 1 mole, if I weigh it, that's the molar mass of water. This is a lot lighter than this, isn't it? Okay, so the molar mass of water actually is 18.02 grams per mole. So the molar mass is always going to be grams of substance per 1 mole of that thing. So grams per mole. And if you're into that little mole raised to the negative first, anytime you see units raised to a negative power, they're just saying it's like in the what we say the denominator. So grams in 1 mole, molar mass. I love it. One of my favorite molar masses is the molar mass of magnesium. It's like, get it? Molar mass of magnesium. So here's how actually all I had to do this morning to get 1 mole of copper atoms was to look at the periodic table. Here's the deal. If I want to know the molar mass for the elements, all I got to do is look at the periodic table. By the way, we're going to, on Thursday, be in that room where there is no periodic table. If we were in here, I'd have to cover it up or something, because one of the things you're going to need to know, and actually I wrote it on your review sheet, is you're going to need to recognize the name and the symbol for some elements. Anyway, if I want to know the molar mass of copper, I just look it up for copper, and it's, hopefully, I think it's 63.45. Sorry. Molar mass is actually, that's that decimal number, 54. 55? 63.55. Okay. 63.55. Now, we said that decimal number, you're like, dude, you told me that's how much a copper atom weighs in AMUs. It is. Okay? But it's also its molar mass. So it's both. It's how much it weighs in AMUs, and it's also its molar mass. All right, water. So that was copper. What about water? How did I know it was 18.02 grams to get 1 mole of water molecules? Well, here's the deal. We worked a problem in here earlier that if you have a cute little water molecule, how do you know how much a water molecule weighs? And you're like, oh, well, however two hydrogens weigh plus however much 1 oxygen weighs. That's how much a water molecule weighs. And we said that was 18.02 AMUs. Okay, that's how much a water molecule weighs. Well, that's also its molar mass. 18.02 grams gives you 1 mole. Okay, so those decimal numbers, okay, for the elements and those masses for the compounds, that's also the molar mass. Okay, so here I have some elements, and there's copper, 63.55 grams for 1 mole. Drum roll. Aluminum. The decimal number for aluminum is 26.98. That's how much in AMUs an aluminum atom weighs. That's also how many grams you need to set aside to get 1 mole of cute little aluminum atoms. Lead, pretty heavy, 207.2 grams per mole, its molar mass. Sulfur, 32.07 grams per mole, its molar mass. Magnesium, 24.31 grams per mole, its molar mass. And chromium, 52.00 grams per mole, its molar mass. So all of those numbers are the decimal numbers for those elements. And they're also their molar mass for the elements. Okay. So here I have, no, you can go ahead and, if you have a periodic table, go ahead and find these. Krypton, iron, manganese, and helium. Actually, these 4, I'm pretty sure, made the cut for, they are fair game on Thursday's test to be able to know the symbol and the name. So what is the molar mass for each of those elements? And you definitely need a periodic table. I would need a periodic table. Although I think I may have told you that elements make great passwords. And then don't forget your units, so the number and the units. I always get manganese and magnesium mixed up. There it is. Number 25, 13. And I got the helium. Is that what you guys got? What do you think? I can't hear you. Oh, thank you. Any questions? All right. Okay. So, here's a few other. This is actually a good review. Remember I said for something like water, we know the molar mass, but first we basically need to find out how much a water molecule weighs. We did that before, and we're going to do it again. So, for instance, what if we have these two compounds, ethane and ammonium chloride, and we're supposed to come up with the molar mass? Well, your hint is to calculate the molecular mass or formula mass, and then those units, of course, would be AMUs, and change those to grams per mole instead. So, here we go. Did we do ethane? We did it. I don't know if we did ethane or not. So how much does an ethane molecule weigh? So we need to take 2 times the decimal number for carbon, which is 12.01, plus 6 times the decimal number for hydrogen, which is 1.008. Okay, and when we add that, multiply and add that all together, that will say how much a molecule of C2H6 weighs. So the rounded to 2 decimals, you get 30.07. 30.07 is how much a C2H6 weighs. But in terms of molar mass, that would be units of grams per mole, not AMUs. So that's how you count. That's how I came up with the molar mass of water. And again, this is kind of a good review for the sort of problem you're going to see Thursday's test. And then the next one. Okay, so in this formula, we have 1 nitrogen, 4 hydrogens, and 1 chlorine. So we would take 1 times the decimal number for nitrogen, which is 14.01. Plus 4 times the decimal number for hydrogen, which is 1.008, plus 1 times the decimal number for chlorine, which is 35.45. And multiply and or add together, and you find out how much, actually that's an ionic compound, so how much a formula unit of that weighs, but its units are going to be grams per mole. So rounded to 2 decimals, I get 53.49 grams per mole. Not bad. All right. So let's do a calculation, okay, involving first the element silver. So my hint for this, I guess, if I have a hint, is you need to first look up on the periodic table, look up the molar mass. And that is different. We've got 2 different elements. We've got first Ag is silver, and then we've got Br bromine. So we've got 2 different elements. The molar mass is different for each element. So if I look up the molar mass for silver, I got 177.87. What is it? 107? Oh, sorry. Thanks. 107.87? Okay, thanks. So mm for silver is 107.87 grams per, actually I'm going to go ahead and do it this way now, grams per mole. That's the molar mass for silver. Now that's like just before I work my problem. Well, let's just kind of eyeball this. Does this make sense? So we have 7.9 moles. And if each mole weighs 107.87 grams, doesn't it seem like I just take 107.87 times 7.9? That's right. That's totally right. And I'll show you what that looks like using kind of the factor label. Using this kind of factor label approach, the number that you start with is going to be here, 7.9 moles over 1. That's the thing we say like you want to convert. And we want moles to cancel, so actually I'm just going to go ahead and take this term here and bring it over. And if I put for silver 107.87 grams over 1 mole, the beauty of that is that with regard to units that cancel, my moles cancel, and I'm left with units of grams, which is great. And that's exactly what we intuitively said to do, so you're right. Kind of like physics problems, in a way. So it looks like we're going to have to round according to 2 decimals. 7.9 times 107.87. Wow. Okay. I got, yeah, this is grams, right? I got two, with 2 significant figures, 850. 850 grams. And if you put like more digits, that would be fine. But actually, that's right. Okay? Let's do the next one. So the next one, we have to switch it up and look up the decimal number for bromine. I'm so going to stick a periodic table in my 79.90. I can make that better. So I'm going to write in purple here, molar mass of bromine, 79.90 grams in 1 mole for bromine. And go ahead and work this. So it seems like we're going to have significantly less than, since it's less than a mole, okay, we're going to have less than 79.90 grams. So actually, if we take 79.90 times 0.0041, that would work. But here's what it looks like using the factor label method. So the first term is 0.0041 moles over 1. And then we bring over the molar mass, 79.90 grams for bromine per 1 mole of bromine atoms. Moles cancel. Left with units of grams. 2 digits again. 0.004. 9.9. I get 0.33 grams. Cool. Okay. Another sort of problem. So that was what we call a moles to grams problem. This is what we call a grams to moles problem. Okay, again, dealing with elements, we have helium and lead. Okay, it's going to be similar. The first thing I'm going to do is go to the periodic table and get the molar mass for these things. So for helium, we decided it's 2.004, 4.003. What is it for helium?
4.03.
Okay. So for helium, the molar mass is 4.003 grams per mole. Now, in this case, notice that I have 5.6 grams of helium. Well, that seems like a little over a mole, doesn't it? It seemed like 5.6 grams of helium, and I only need 4.003 grams of helium to have a mole. So I have a little more than a mole. So my answer should be a little over 1. So if you're dividing numbers and such, you don't want to take 4.003 and divide it by 5.6 because you're going to get less than 1, right? So actually it's going to be the other way around. I'll show you how that works, though. So in this case, we're going to put the 5.6 grams of helium. I'm going to put it over 1. Now, the beauty of this method is that I want these units, I want grams to cancel. Okay, so can you see where actually I'm going to use the molar mass, but I'm going to flip it. So the next thing you're going to see right here basically is the molar mass flipped. So if I go ahead and for my second term, if I put 1 mole over 4.003 grams, the beauty of that is now my grams are going to cancel. And that's really why we do this, work problems this way. So you kind of have you have a choice this semester, okay, of how you work it. But if I take 5.6 divided by 4.003, then I get a number bigger than 1. There's also ratios and things like that, but give it 2 decimals, 1.4 moles. I'll buy that. Seems reasonable. And then let's do the last one. Dealing with lead. So is that the 207 molar mass for lead? PB? 207.2 grams per mole. And in this case, let's see, oh wow, we only have 12 grams. So you're like, dude, 13 grams. So you definitely have less than a mole, right? So we definitely don't have a mole. So our number's going to have to be less than a mole. So we know if we take 207.2 divided by 12 or 13 or whatever, you're going to get more than 1. So actually what it's going to be is this 12.98 divided by 207.2. That is actually how we're going to get to our moles. And this is what it looks like setting it up with the factor label method. So 12.98 grams over 1. And then again, anytime you have this sort of problem, from grams to moles, we got to flip the molar mass. So that's what we're going to do. We're going to take that molar mass, and we're going to put for lead, 1 mole over 207.2 grams. And then the beauty here is that our units of grams cancel. Left units of moles. And if we take 12.98 divided by 207.2, this time it looks like I get to go with 4 digits. So I got 0.06264. And units, of course, would be moles. Seems reasonable. Okay, I'm going to go ahead and write, instead of doing an assignment from your textbook, I'm going to write it up here. Oh, did you try to decide? That'll work. Okay, so just for the elements, we'll do each of those 2 types of problems. So, let's see. So this one, how many grams contain how many grams of carbon contain, let's go with 0.0395 moles, carbon atoms. So basically you're going from moles to grams. And then the next one, from grams to moles, is how many moles of gold atoms are there in 57.3 grams of gold. I think that looks right. So how many grams of atoms contain? How many moles of gold atoms are there? I think that looks good to me. Okay? And that should wrap us up for chemistry. Awesome!